Today's lesson is going to be over heat capacity and calorimetry. This is one of the more complicated topics that we cover in AP Chemistry, and this is often going to be a calculation that you see as an FRQ on the AP exam in May. So heat capacity is how much energy it takes, and typically it's in joules, but energy is going to be measured in joules or kilojoules if there's a whole lot of energy, required to raise the temperature 1 degree. And it's change in temperature, so it doesn't really matter if it changes 1 degree Celsius or 1 Kelvin because they're equivalent. So if we leave it in Celsius, it's going to be 1 degree if we take the change in temperature. If we change it to Kelvin, it's still going to be 1 degree if we take the change in temperature. And so the temperature unit doesn't matter. Sometimes you're going to be given Celsius in the problem. Sometimes you're going to be given Kelvin. In this one, you do not have to convert like you do with gas laws. You don't have to convert these all to Kelvin. You can just take whatever the problem gives you. So the equation is going to be CP, which stands for specific heat capacity. Sometimes it's just represented as a C, uppercase, is equal to joules over grams times your degrees Celsius. The C sometimes has that lower script, the subscript P for constant pressure. Your mass is going to be measured in grams, and again, your temperature, it really doesn't matter. The equation for this is going to be a combination of those units will combine to give you the specific heat capacity. It takes all those things. It matters how much you have, that's the grams. It matters about the energy, that's going to be your joules, and then it matters about the temperature change, and that's going to be your degrees Celsius or your Kelvin. There's also something called molar heat capacity, and it is in essence the same type of setup, except for it's going to be joules per mole times degrees Celsius or Kelvin. In this one, there's different ways that AP will have us solve out for the molar heat capacity. You're typically going to see that specific heat capacity in grams. So if we're talking about the heat capacity of something, substances with a higher heat capacity value have lower changes in temperature with a given amount of heat. So water, for example, has a specific heat capacity of around 4.18 joules per gram times degrees Celsius or Kelvin. If you notice these metals, none of them are nearly that high. The highest out of these four metals is aluminum at 0.897. Water is, like I said, 4.18 or 4.2 depending on the problem. And so this is the reason that whenever we have long periods of below freezing temperatures, that it takes several days of below freezing before water bodies start freezing. I live in Tennessee, and we rarely see ice on our ponds and lakes because we don't stay below freezing for an extended period of time. Whereas if somebody lives further north, where temperatures stay low for most of the season, that's where water bodies are able to freeze. Our lakes and ponds are able to freeze, and they freeze deep enough that people can ice skate on them. That doesn't happen down here in the South because if we do get any sort of icing on a lake or a pond, it is very, very thin. It's because it takes so long. It takes 4.18 joules per gram Kelvin. That's a lot of energy to change each mass by 1 degree, whatever the temperature scale is, Celsius or Kelvin. Same deal in the spring. If you do have water bodies that freeze, it takes forever for them to thaw because it's the same process. They're still having to take in that amount of energy to thaw out and melt that water. So in this question, we have about metal. It is asking us if equal masses were used, which metal out of aluminum, iron, lead, and cadmium, which metal can absorb the most heat before the temperature would increase by 1 degree Celsius, and justify your answer. Again, that question is literally asking for which one has the higher heat capacity, because if they have the same mass and they have the same temperature scale, if I go back to my equation, then the mass and temperature are same. The only thing that can be different is that amount of energy that it's requiring to be able to have that specific heat. So the one that can absorb the most before a temperature change, you can also word that in the way which one is going to be the hardest to change the temperature, which one's going to require the most energy. And so we're going to do this one in a claim evidence reasoning style. And so if I come down here, my claim is aluminum can absorb the most heat. And heat is going to be measured in that unit of a joule. My evidence is because aluminum has the highest heat capacity. Up here, it's going to take 0.897 joules per every gram Kelvin. And my reasoning is if I have a higher heat capacity, indicates the ability to absorb and this could be absorb or release. It just depends on, this one saying how much can it absorb, depends on if it is heating up or cooling down. So we're talking about heating it up. So absorb more heat before the temp rises. If the question instead said which metal can absorb the least heat, we would look at these and we would choose lead because it has the smallest number. So these numbers, if everything else is consistent, if it has the same mass, we're talking about the same change in temperature, then those values can be figured into being just how much energy is it going to need. So typically, the equation is going to be rearranged, and you're going to use it in this format. This equation has just been rearranged to solve for heat, which is going to be represented by the letter Q. And so it's going to be Q is equal to mass times your heat capacity, your specific heat, times your change in temperature. Q is your heat, which is in the unit of joules. M is your mass, which is in the unit of grams. Cp is your specific heat capacity. Again, it's going to be joules per gram times Kelvin. And it might be given to you in joules per gram times Kelvin or joules per grams times degrees Celsius. Doesn't matter. And temperature does not matter. You leave it in Celsius or Kelvin. Don't waste your time doing temperature conversions with these types of problems, because we're going to be taking the change in temperature. And so then it ends up canceling out. The change in temperature will be the same. And then if we look at the other equation, this is going to be our molar heat capacity. It's still Q is equal to moles times your specific heat times your change in temperature again. So let's do just a basic question, and then we're going to work our way up to more complicated. So this one is saying if you have 200 grams of water is to be heated from 24.0 degrees Celsius to 100 degrees Celsius to make a cup of tea, how much heat in joules must be added? My grammar there is terrible. The specific heat of water is 4.14 joules per grams times degrees Celsius. Oh, that's where my ED is. It got separated from over there. And so now I just have a weird ed at the end of it instead of added. Anyways, so we're going to work this problem out. And it is asking for how much heat. So we are going to be using that equation that I showed you just on the last slide. Your Q is equal to your mass times your specific heat times your change in temperature. Now, I will tell you that on the AP exam for both the 2025 and 2026 school year, this question was an FRQ, and a question similar to this, using this equation, was your sig fig question. A majority of students missed it because the question was complicated. It was more complicated than this one, but it was using this equation. The biggest mistake people make is they do not round correctly when it is a multiple operations question. So in a question like this, change in means that I am going to do, anytime you see that delta T, it means change in. And it always means whatever the value is, its final minus whatever the value is, its initial. So this is change in temperature. So my final temperature minus my initial temperature. That is a math operation that you have to round before you go to the next step. So let's substitute all of our numbers first, and then we'll go through and solve it out. So my mass is going to be 200. Remember, write numbers exactly as they are so you don't mess up on sig figs. 200 grams. My specific heat, it tells you, it will always tell you that number. You do not have to memorize them. And sometimes AP uses different numbers. Sometimes they'll use 4.2 instead of 4.18. It doesn't matter. They all come out to about the same. You just use whatever AP gives you. This whole thing is the unit, joules per grams times degrees Celsius. And then my change in temperature is always final minus initial. AP is not going to tell you to do change in temperature. That's something you need to be familiar with. But in sciences, you're going to see change in something a lot, whether we're in chemistry or even in physics. And so we're going to do 100 degrees Celsius minus 24.0 degrees Celsius. So before I do anything else, I am going to round my answer for the temperature before I start doing the rest of the math. Because what happens is if you're only using your calculator, you can do math, but your calculator does not do sig figs. That's where your brain has to come in. So when I'm doing 100 minus 24.0, when I first start teaching sig figs, I teach my students to line up the decimal. So 100 doesn't have an inserted decimal, but it does have an understood decimal at the end of the 100. I don't add one because that changes significance. So then I'm going to do minus 24.0. When we were doing addition and subtraction, it is based on places past the decimal. You round to whichever one has the least places past the decimal. 24.0 has a place in the tenths. 100 has no digits past the decimal. It only has a digit in the ones place. So I'm going to cut this answer off at the decimal. So when I plug it into my calculator, I do 100 minus 24.0, and it gives me 76. And if I want to include a 0 there, I can, but that is not significant. So my answer is 76 degrees Celsius. So now I'm going to do my math in my calculator. So I'll do 200 times 4.184 times 76. These units will cancel with your unit for specific heat. It's a good way to check yourself to see if you're doing your math right. So I should cancel grams and grams. Celsius and Celsius will cancel. If this was Kelvin, they would still cancel because we are doing change in. And then I am left with my unit of joules, which makes sense because I'm solving for how much heat. So I'm going to write out my answer for my calculator. My calculator gives me 63,536. Make sure you're careful on the AP exam and you are rounding to the correct unit. This one says heat in joules. So these are my joules. That's what I have. But it is not rounded to the correct number of sig figs yet. So then I look at these. This has 1, 2, 3, 4 sig figs. This has 1, 2, 3. And this has 1, 2. This is where people make a mistake is they plug this in the calculator and they put in parentheses on their calculator and they get a final answer of this. But then they make the mistake of going back to these numbers and using these for sig figs. Well, if I was just looking at these on their own and I looked at that number, I would think that only had one sig fig, and I might screw the whole question up and round this answer to one sig fig. But I don't, because when I did this math operation of subtraction, I had to round this answer, and this is where my sig figs come from. So I need to round my answer to 2 sig figs. I cannot round it to just 64. I have to keep that 6 in the 10,000s place. So it's going to round to 64,000 joules. So be real careful on sig figs. I don't know that AP is going to do a question like this again as their sig fig, but the fact that for 2 years they've done it and most of the nation has missed it, they might do it again to see if you guys will figure out how to round with these types of problems. If there's multiple operations, you have to round before you go to the next step. So in this question it gives us a data table. And this is more like the type of question we've seen on the AP exam in the FRQ section where they give you a data table from a calorimetry experiment. And they're asking you to figure out from that some data. So it says, in an experiment to determine the specific heat of a metal, a student transferred a sample of metal that was heated in boiling water into room temperature water in an insulated cup. That's really all calorimetry is how much energy transfers from one object to the next. This one is using metal and water. The insulated cup hopefully stops energy from being shared with the surroundings. And so the student recorded the temperature of the water after thermal equilibrium was reached, which in a previous video I've talked about. Thermal equilibrium is once they have transferred out their energy and reached that same final temperature. The data are shown in the table above. Based on the data, what is the calculated heat Q absorbed by the water reported with the appropriate number of significant figures? Now you have to be careful because the question is asking about the water. My data table is going to have stuff for both the water and the metal. So you need to be sure that you are looking at the data and pulling the right data for the question. So it is asking me to use the Q equation again. So I'm going to work it down here. Actually, I'll work it here. I have a little bit more room. So I'm going to do Q is equal to. So my first thing is mass, but again, I need to make sure I'm looking at stuff about water. And so my mass of my water was this 50.030. I have to use the specific heat for water, which in this one, it gives me 4.184. Like I said, AP gives you all kinds of different numbers for the specific heat of water. You just have to know that you're using the right one. Whatever it gives you in the problem, just use that one. And then my change in temperature. So this is going to be my final temp minus my initial temp. It always has to be final minus initial. So down here's the final temperature. The final temperature, because of thermal equilibrium, is going to be the same for the metal and the water. And so I'm going to use the final temperature of 32.80 minus, and I'm running out of room, so I'm going to write it down here. If I look back at my initial temperature of the water, again, be careful because you have metal and you have water. The initial temperature of my water is 24.95. So then I'm going to end up with Q is equal to 50.003 grams times my 4.184 joules per grams times degrees Celsius times, I want to subtract these two. So this time I'm going to do 32.80 minus 24.95. And again, the rules for subtraction and addition is based on places past the decimal. That's the reason we need to write numbers exactly as they are in our problem. Because if I left off that 0 for 32.80, it would give me an incorrect number of sig figs. So since both of these have the digits in the hundredths place, then that's how I'm going to round. So my final change in temperature is 7.85, and that is going to be degrees Celsius. So now I'm going to multiply these out. My grams are going to cancel. Celsius is going to cancel. So then I do 50.003 times 4.184 times 7.85. And in my calculator, it gives me a big number. I'm going to write the biggest that is down here so that we can look at how we need to adjust it. So I have several digits after. It goes 18533. So sig figs, this has 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3. I round to whichever one has the least number of sig figs. So I need 3 sig figs. So I'm going to keep the 164. I cannot leave it like that because the one has to stay in the thousands place. So I'm going to include a placeholder 0. And so my correct answer is going to be 1,640 joules because of my energy and my sig figs. So this one's a little bit trickier, and I'm going to show you a way algebraically to solve it that makes it a little bit easier and not quite as intimidating. So it says, for an experiment, 50 grams of H2O has been added to a coffee cup calorimeter. Again, calorimetry is just how much energy did it start with and how much heat transferred, so we can figure out the energy. As shown in the diagram above. I don't have the diagram, it's not necessary. This is the initial temperature of the H2O was 22.0 degrees Celsius, and it absorbed 300 joules of heat from an object that was carefully placed inside the calorimeter. Assuming no heat is transferred to the surroundings, which is the purpose of the styrofoam with the coffee cup, it says, which of the following was the approximate temperature of the H2O after thermal equilibrium was reached? Assume specific heat capacity of H2O is 4.2 joules per grams times Kelvin. Again, I got a different specific heat capacity for water. This one's in Kelvin, not in Celsius. Doesn't matter. We're still going to use all the same stuff. So it is asking me not about what is my specific heat. It is not asking me about how much heat I have. It is asking me what my change in my final temperature was. So the way that I recommend solving this is you are going to use your specific heat equation that Q is equal to, but let's go ahead and start substituting in. So I'm going to use my Q. So I'm going to use 300. Be sure you put the decimal because that makes it have 3 significant figures, is equal to, it tells me my mass of my water is 50.0 grams. This time I'm using 4.2 joules per grams times Kelvin. And I'm just going to solve for change in temperature. I'll explain where we figure out what the final temperature is, because that's what it's asking. It says the approximate temperature of the water after thermal equilibrium. So it's actually asking me for final temperature, but this is going to make it algebraically easier for you. So to solve this out, I'm going to divide 300 by my 50 and my 4.2. So I'm going to set that up over here. So mathematically, you're going to end up with it looking like this. When I divide this out, my grams are going to cancel still, and the joules are going to cancel still. So I am solving for my change in temperature. So let's plug that in our calculator. So 300 divided by 50 and 4.2, you can plug that into your calculator several different ways. You can use parentheses, or you can do 300 divided by 50, enter on your calculator, and then divided by 4.2, enter. It doesn't really matter. You just need to be careful and make sure that you are telling your calculator to do the correct order of operations. If you just do 300 divided by 50 and you do times 4.2, a lot of times it will incorrectly do it. It'll do 300 divided by 50, and then it literally multiplies that answer times 4.2, which is not mathematically what we're doing. So just be careful with how you plug it in. So when I do that, it gives me 1.428571429 on my calculator. Then I do sig figs. This one is going to have 3 sig figs. This one's going to have 3. This one has 2, so I'm going to round to 1.4. And we can say Kelvin. Here in a minute, it's going to change over to Celsius because it doesn't matter. The change in temperature will be the same. So if you want to go ahead and think that that is degrees Celsius, that'll make it easier in a minute. When you start plugging in numbers, you get confused about the units. So once I know the change in temperature, then I can use my equation, which is change in temperature is equal to TF minus TI. I now know my change in temperature is my 1.4. I'm going to use degrees Celsius. I need to know my TF, and I know that my initial temperature was that 22.0. So I've got to solve for the TF. To do that, I'm going to add 22.0 degrees Celsius to both sides. That'll cancel it over here. So then my TF is going to be equal to 1.4 plus 22.6. 22.0. I can't even read my own writing. And so my final temperature is going to be 23.4 degrees Celsius, which is going to give me letter D. You could have algebraically plugged this in up here and had your final temp and initial temp and solved it out that way. It just is a lot harder for some people, the algebra that way. I found that if I do it this way, it's a little bit easier for me to do. You do need to understand that the change in temperature has its own equation. Your delta T is going to equal to your T final minus your T initial. And you can do this also if instead we were not talking about water, if we were talking about the metal, we could also do this same process. So, with this chapter, we're getting into thermodynamics, and the first law of thermodynamics states that energy cannot be created or destroyed, it is only transferred. So my heat loss numerically is going to be equal to my heat gained. The difference is that often your heat loss is going to be negative, your heat gain is going to be positive, but as far as the magnitude of the numbers, they're the same. Your amount of Q loss will be the object with the higher temperature, while the Q gained is the object with the lower temperature. So most of the time, we take a piece of metal that's hot and put it in water. So the metal is typically my Q lost, and the water is my Q gained. But there's different types of questions with this. Sometimes we might be talking about salts and solutions. There's a lot of different things. So it's just always whatever is warmer is going to lose energy. And it's not losing, it's transferring, because we can't create or destroy, but it's transferring it. And then the other one is going to gain it. So let's work out a problem like that. So this one says a 12.48 gram sample of an unknown metal is heated to 99.0 degrees Celsius, was then plunged into 50 milliliters of water of 25 degrees Celsius water. The temperature of the water rose to 28.1 degrees Celsius, assuming no heat is lost to the surroundings. It's asking us questions. So one thing that you have to know for this, and I'll get to it in a minute, is first it's asking how many joules of energy did the water absorb. So we're going to start by doing our Q equation for water. So Q is equal to, so my equation for Q is going to be mass times your specific heat times change in temperature. And I have the mass of my metal, but I don't actually have the mass of my water. But we do, because if we have pure water, then for every 1 milliliter of water, it is equal to 1 gram. So since I have 50 milliliters, it is the same thing as saying I have 50.0 grams. My specific heat of water is 4.18 this time. Again, just use the number they give you. And my change in temperature is going to be for the water. So my water's final temperature was 28.1. My water's initial temperature was 25. Oh, it did not change to my eraser. Okay, so if I do this part, if I do 28.1 minus 25, again, I've got to be really careful and make sure that I'm keeping my sig figs correct. And so both of these have a digit in the tenths place, so I'm going to round to the tenths place. It's important to include all zeros. We don't want to change any number to change the significant figures. So the difference between these two is going to give me 3.1 degrees Celsius. I don't have as much room on this slide, so I'm going to try to shorten some of the steps. So now I'm going to do 50 times the 4.184 times the 3.1. Again, if I want to look at my units to cancel, I'll be left with joules. So I'm going to do 50 times 4.18. Times the 3.1. Sorry, I couldn't find my 3.1 on my screen. So then it's going to give me 647.9. But I have 3 sig figs, 2 sig figs. So I need to round that number to 2 sig figs. So my final answer is going to end up being 650 joules. Now, the next question says, how many joules of energy did the metal lose? So if I go back to my previous slide, my amount of energy lost is going to be equal to my energy gained. They are numerically equal. The sign is different. And so the amount that I have gained for the water was 650 joules. That means the amount that the metal lost was a negative 650 joules. They are numerically equal. The only thing is different is which one loses and which one's gains. Then it asked me for the specific heat of the metal. So now I'm using that specific heat equation, which is Cp, or C is equal to Q over my mass times my change in temperature. So my energy is going to be this negative 650 joules. My mass, this is now for my metal, I'm going to come back up here, is 12.48 grams. And then my change in temperature for the metal is my final temperature is 28.1, because when they hit thermal equilibrium, they will hit the same temperature at the end. Any of these problems about heat capacity and calorimetry, when you have put two things in a container in the same area and there's no heat being lost, that's why we can do this number thing, because no heat was lost, but the final temperature will be the same final temperature for both the substances. And so I have 28.1 for my final temperature. Its initial temperature was 99.0. So then if I do 28.1 minus 99.0, I'm going to end up with a negative 70.9 degrees Celsius. And that is good because that cancels out my negative up here. Because specific heat is always just a positive number. You can't have a negative specific heat because it's just a certain number of how much energy does it take per 1 gram, changing 1 degree Celsius, or however we want to define it. So this has to be a positive number. So let's say you didn't have the negative up here, and then you had a negative here. At the end, you would have to figure out that this had to have been a negative value, because this has to cancel out, because your specific heat is always just a positive value. And so mathematically, I'm going to do 650 divided by 12.48 divided by 70.9. And I need 2 sig figs because of my 650. It only had 2 sig figs up here. And so this time my units are combining because I'm getting specific heat. And so I end up with 0.73, and my unit is joules per grams times degrees Celsius. So when we're talking about calorimetry, the situations are going to be about the same no matter what. You're going to have two things that you add together into some sort of insulated container where no energy or no heat is lost. And you're always going to have, in this case, it was a metal and water, but it could be different substances. But the hot thing is going to transfer its energy to the colder thing, and their final temperature is always going to be the same. They are going to have an equal amount of energy that is absorbed and lost. One will be positive, one will be negative. Q can be positive or negative. C or CP, your specific heat, has to be a positive value. So you can sort of check yourself on your setups. If you think you did something wrong, you cannot have a negative specific heat. So this is just sort of a continuation of the last one that I was talking about. Calorimetry is really just the process of measuring how much heat is transferred. And in the problems, it's always going to talk about using a styrofoam cup or some sort of insulated container to control the transfer of heat. And we're going to have that negative Q metal because it's losing, and the water is gaining the energy. So I'll have a really hot piece of metal, I'll put it into the water, it's going to transfer it. And those are going to be equal in magnitude and opposite in sign. So this is a type of question that we'll see on the AP exam. This is what we've seen the last few years, where it has some questions and it gives you data and you have to interpret the data. This is usually an FRQ question. And so in this one, it says the mass of the calorimeter in the water, and the mass of the calorimeter, water, and salt. So this one is not a metal problem like our last one, this right here, what it's doing is making a solution. It's making a saltwater solution because we've dissolved salt in water. We have our initial temperature and our final temperature. So we have to figure out, is this dissolving process exothermic or endothermic? So my temperature started out as 20 and my final temperature is 36.5. So that temperature increased. The energy had to come from somewhere because in a calorimeter, it is all enclosed. So there's not an effect from the surroundings. It's all coming from the system. And so is the dissolving process exothermic or endothermic? It is going to be exothermic. And the reason is the temp of the water, which is what we're measuring. It's the solution at the end, the temp of the water increases. Calculate the mass of the solution used. So we got to figure out how much solution was used in this problem. So this here is where we have the mass of the calorimeter, the water, and the salt. This is just the water. This is just the calorimeter. And so to figure out how much of the water and salt I have, which is my solution, I'm going to take this 61.54 minus my 11.31. And again, this is subtraction. They both have two places past the decimal, so my answer has to have two places past the decimal, so it's going to be 50.23 grams. From there, we're going to do letter D. So letter D says determine the change in temperature. Again, change in temperature is always final minus initial. So I'm going to do 36.5 degrees Celsius minus my 20.0 degrees Celsius. When I subtract those out, I'm going to end up with 16.5, which is correct because I got to have one place past the decimal. And it's going to be my change in temperature. Letter E says calculate the moles of calcium chloride dissolved. Well, we were sort of missing the first part of this question where it would have explained that that solution actually is calcium chloride. And so it is asking about that. It tells us that the molar mass of calcium chloride. AP does this a lot to make your math faster. They want to see that you understand how to do the conversions, but they aren't worried about if you can add up the mass of a compound, so they give it to you to make it faster. But you do have to understand what this means with them. They often give it to you in the form of grams per mole. And so I have to figure out the amount of my calcium chloride dissolved. So for this one, I'm looking for just my salt, not the solution. Remember over here it asks calculate the mass of your solution that's used. This one is asking for the salt specifically. And so for this one, I'm going to have to start by finding out how many grams of salt I have. So I'm going to do 61.54 grams minus the 56.57 grams. And that is going to give me 4.97 grams of CaCl2. That is my salt alone. This one is asking just for the salt, just for the CaCl2. And so then I've got to do a basic gram to mole conversion. So I know that I have 49.7 grams of CaCl2. This is saying that I have 110.98 grams per 1 mole. That's what it means by molar mass. And so I have 110.98 grams of CaCl2 per 1 mole of CaCl2. This has 3 sig figs, so when I divide this out, I need 3 sig figs. So I end up with 0.0448 moles of the CaCl2. So then it says calculate the molar heat of solution, and by the end, I need to get it into joules per mole. For these types of problems, I told you that a lot of times when they ask you about molar heat of solution, you have some other information that's given to you. And so in this, we are going to solve for Q first. And so whenever I have my Q, then I'm going to do my mass of my solution, because this one is going to go back to the molar heat of my solution. This was for the moles of my salt. And so for the first thing, we got to figure out how much energy, what happened here with the solution. And so I'm going to start with my value for my previous slide my 50.23 grams of my solution. Since the solution is in water, we're going to be using the specific heat of water. Again, this would have been given in the paragraph that you're not seeing in this question. They would give you the specific heat, and so you would just have to look it up. It'd be back in the original prompt. And then my change in temperature, I already figured out. That's why AP a lot of times will make you do these where you have like little baby steps and you just have to go back and pull information from those baby steps. So my Q is going to be, I need 4 sig figs, 3 sig figs, 3 sig figs. My Q is going to be 3,460 joules. So then it's asking me for my molar heat of solution. And we have to see here that we said initially that the energy is exothermic. And so the amount of energy in this one, the Q lost and the Q gained. And so since this was all a solution in a container, then the energy is being sent out. It's the exothermic. It's measuring the energy that's being sent out. And so this is going to be a negative value. And then the thing that it wants us to have is it wants our final answer to be in joules per mole. So this is how much energy, but I haven't incorporated my amount of moles. And so I'm going to take that number, which I wrote wrong, and I'm going to divide it by my number of moles. AP does this a lot where they make you take a lot of information and combine it together. And this is really complicated. For the most part, I think most of it was pretty straightforward. I feel like figuring out it was exothermic was okay. Figuring out the mass of the solution from the data is okay once you understand how to read the data. Changing temperature is okay. Even doing the gram to mole conversion. Of course, if you had had that prompt, that would have been before letter A. It would have clarified a lot of that stuff. I think you could have done that. This last one is a little bit trickier, and this is where practice makes it easier. And so then I'm going to do the 3460 divided by 0.0448. I need 3 sig figs because this has 3, that has 3. So it ends up being a negative 77,200 joules per mole is my molar heat of solution. If they give you units, they're usually given an indicator of how to solve it. And sometimes we have to do that in more than one step to be able to solve it out. And since it's asking for the solution, then you have to go back to the mass of your water and your salt because they play into it because it's per amount of gram to raise it up. And so your final answer is going to be the negative 77,200. And again, that makes sense because if this reaction was exothermic, then that amount of energy needs to be a negative value because it gave off that energy. So with the specific heat capacity and calorimetry, like I said, these are pretty complicated questions. AP does give you these the Q equation. The rest of the stuff we sort of have to just problem solve and figure out on our own.